Hello and welcome to the third part of hypothesis testing. In this video we'll look at critical regions and find the critical region for a test. Let's explain what it is. Let's go back to the original question we had in the very first video, where x was the number of heads we got when we flipped a coin 10 times. And we said that the null hypothesis was just that the coin was fair, so the probability was just 0.5 of getting a head. Then the alternative hypothesis was that we thought the coin was maybe biased towards heads because I think we got 7 of them in the first video. And we still do a 5% level of significance. In fact, that's always the case with S2. Now this time we're going to find the critical region. See, normally in the questions we've been doing before, I've now told you an observed value. So in the first video it was that x equals 7, and we test to see whether x equals 7 would reject H0 or not. Now what we're looking to do is find the critical region. Now the critical region is just the values of x. The values of x such that the probability of getting, in this case, bigger than x, because we're looking at bigger than 0.5, of that happening is really small, being less than our level of significance, less than that 5% up there. What we're really doing, you see, is asking how big does x need to be? How many heads do I need to get out of 10 before I would reject my null hypothesis, and actually my alternative hypothesis is more likely. So this is really the region of x values where the null hypothesis, H0, is rejected. So because we're doing a bigger than 0.5, it's going to be a bigger than there. So we're going to look at maybe x is, well, we know 7 isn't rejected, so maybe 8 or 9 or 10, and it would be rejected. You can kind of imagine it as if you draw a picture where you have here this x values between 0 and 10 that you possibly could get, and here you have sort of the probability of x being equal to x, and then 5 you've got the maximum, and it kind of goes up and then down again. And we're really asking is, well, how many of these values could I take, and where until this value is still less than 5%. We want that value to be less than 5%. We want the biggest number of numbers in there, and those numbers there are going to be ones that end up getting rejected. So really looking for the smallest x value that achieves this. So what we're trying to do, we're trying to work out the probability of x being bigger than x being less than 5%. Okay, so this thing here is the same as 1 minus the probability of x. Now, we have to take 1 away from that. If it was like a 9, we put an 8 there. Or 10, we put a 9 there, or 7, put a 6 there. That's immediately less than 5%. Okay, so we could move these two things around, do 1 minus 5%, 5% is 0.05, and then put this on the other side. Just trying to rearrange this so we can look up. We can look at ones that are less than, you see, we can't look at ones that are more than. So this is 0.95. So we're looking to look up in our binomial table a value here, such that this is bigger than 0.95. That's the idea. So so here we go. Here's our table, n equals 10. Go across, we're looking at the probability of 0.5 column, and we're looking at for the first time when this is bigger than 0.95. So 8.2, 9.4, 8.2, 0.94, 0.98 is the first time just there. So that's at the value of 8. So when x equals 8, we have bigger than 0.95. So let's just write it down. Probability of x is less than 8 is equal to 0.9893. That's the first time it's bigger than 0.95, which means that this number here, x minus 1, must be equal to 8. Which means x is equal to 9. So the critical region is when x is bigger than 9. As in when x is 9 or 10, we would reject H0. Can't be a fair coin, probably more likely to be biased, and go with H1. So for those high values of x, we will reject H1. So try drawing a coin 10 times and getting 9 or more of them heads. It's difficult to do. You have to do it very many times. In fact, the chance of it happening is less than 5%, which means probably if it does happen, your coin is probably biased. Or you're Darren Brown, you've been sitting there flipping coins for a long time. Let's just do this for a less than so you can see the other direction. The other direction is a lot easier. Let's go for the same thing again. Number of heads again, but this time we'll have h0 be 0.5 and h1 be less than 0.5, so we've seen the other direction. So my critical region is still going to be 5% lower significance. We're still trying to find the critical region. So this time we're looking for the x value such that the probability of x being less than x, because we're doing with less than 0.5 now, and we still want it to be less than 5%. We're still looking for the raise of x, which would be in the critical region, therefore rejecting h0. That's why it's less than 5%. So this is easier because over here we had to do some rearranging to get a less than, because we can look less thans up. Here it is already a less than, so we're just going to look it straight up. That's good grammar there. So we go over here, we find 0.5 again, and n equals 10. And we're going down, we go, oh, there's 0.054, so that's too big. So that one there is the one I want, less than 5%, but I want the bigger one that's less than 5%. So x equals 1 will work for me. So the probability of x being less than or equal to 1 is equal to 0.0107, or if you like, 1.07%. So x being less than 1 is the critical region. Done. I suppose the last thing we could do is a two-tailed critical region, like an x is less than this or x is bigger than that, because both these are one-tailed, one side, 0 and 1 or 9 and 10. If we did that, then we'd be dealing with null hypothesis being 0.5 and our alternative hypothesis being just not equal to 0.5. Still 5% level of significance. This time we're looking for two values, a sort of smaller one and a sort of bigger one. But this time each tail has to be less than 2.5%, as we said before. So we're looking now for the probability of x being less than x being less than 2.5%, and the probability of x being more than y being less than 2.5%. So let's have a look at our table. So that number there, 0.125, that is less than 2.5%, and that one is bigger than 2.5%, so it's the same value. Oh, that's interesting. So x equals to 1 will work here, because probability of being less than 1 is 1.7%. That's one side. And on the other side, we're looking for, we're looking for the 1 take 2.5%. So if you like, 1 take 2.5%, otherwise known as 0.975. So the first number that's bigger than 9.75. Now that is there, 0.983. When x is less than 8, we've got 0.9893, which is bigger than 0.975. Of course, if it's 8 here, to get a bigger than, we need to use the probability of x being bigger than 9 will be equal to 0.0107. This is where people often make mistakes, because they stop doing all the working out that we had over here, where the x goes to x minus 1, and you start trying to do things quickly and think, oh, it's to that number. You look up the number and get the 8, but then don't remember that because you're doing bigger than now, you want a 9, not an 8. That's the most common mistake. So we want the 9 because that gives me a percentage here that's less than 2.5%. So here we're saying that y has to be bigger than 9. So either x is less than 1 or x is bigger than 9. That there is my critical region. This is two-tailed. Turns out in this two-tailed test, because these critical regions were already quite a low percentage, that we don't have different ones, but it's entirely possible for them to be the same two as before, or different, depending on what the exact percentages you get here. We had 1.7%. If our percentage had been like 3%, we'd have to go down another one. The critical regions would be further out. It just sort of depends on the question. You should be able to go at all the exercises now, although you may find that some questions are still difficult. Well, just ask.